Welcome back. Do we have sufficient amount of renewable energy generation sources available to meet our enormous energy demands? How much energy or power can the most important renewable energy technologies deliver? In this lecture, we study the renewable electricity generation based on hydroelectricity. The learning objectives are: understand the basic physical principle of hydroelectricity, calculate and analyze the important performance metrics of a hydroelectricity plant, like conversion efficiency, the energy yield, capacity factor, surface power density, the CO2 emissions, and the energy payback time of a hydroelectricity plant. And to be aware of the pros and the cons of an hydroelectricity plant. We will start with the sun. The energy source behind the hydroelectricity dam is the sun. Let me explain. Sunlight heats oceans, lakes, and rivers. It provides energy to evaporate water. The warmed surfaces will heat air and moisture further and triggers the upward movement of moisture due to convective lifting. The moisture condenses at higher altitude, resulting in the formation of clouds. The water vapor in the clouds precipitates as rain and snow that is then collected in a large reservoir through streams and rivers. Due to this precipitation, the reservoir fills up to a certain height. In this whole cycle, the water has been moved from lower to higher altitude using solar energy. The water has gained potential energy. At an hydroelectricity dam, this gravitational energy is stored in a water reservoir, like this artificial lake you see behind the dam. This stored potential energy of water is converted into electricity. The water flows down a penstock, and the potential energy is converted into mechanical energy by a rotating turbine. The turbine is connected to a huge electric generator to convert the mechanical energy into electrical energy. And the generator is connected via transformers to the electricity grid to deliver electricity. Let's take a look at the factors that determine the primary energy potential, conversion efficiency of the hydroelectricity generator system, the energy yield, and the capacity factor of such a dam. Hydropower uses the potential energy of the water stored in the reservoir. Potential energy is the energy that is released by dropping a certain mass from a certain height, as described in the following equation, where E pot is the potential energy expressed in the unit Joule, mW is the mass of the water expressed in kilograms, G is the gravitational constant of 9.8 meters per square second, and H is the height difference between the source and the outflow of the dam, often referred to as the hydraulic head. Energy per time is power. We can also express this as the potential power, and as you can see, instead of mass, we consider the mass per time, or in other words, we use the mass flow. The mass flow is equal to the volume flow V multiplied by the mass density rho of the water. The total mass available is strongly related to the amount of rainfall and the total area from which the reservoir collects the water. This is referred to as the catchment area, here enclosed by the red line in this example. This is the total area where the water, typically from rain or snow, collects and drains downhill into rivers and lakes. Downstream, an hydroelectricity dam can be constructed, for example, at the red dot here in this example. Behind an electricity dam, an artificial lake is created, which acts as the water reservoir, where all the water flowing downhill from the catchment area is collected. If we know the size of the catchment area, we can estimate the potential energy of a certain region or dam. The annual water mass available, MW, expressed in kilogram per year, is related to the precipitation according to this equation, where R represents a precipitation, which is the amount of rainfall in cubic meters per square meters per year. Rho is the density expressed in kilograms per cubic meters, and A is the catchment area expressed in square meters. Part of the water that falls down in the catchment area can be absorbed, for instance, by soil or absorbed by vegetation or evaporate before being collected at the inlet of the hydroelectricity dam. The water that is disposed through the spillway can be considered as a loss as well. Spillways are a kind of safety valve of a dam to prevent flooding of the water reservoir. And all these loss processes are included in this dimensionless loss factor. The conversion efficiency is defined as the ratio between the output power and the input power. The output power is the amount of electrical power generated, and the input power is the theoretical potential gravitational power that can be lifted by the water flow. Energy conversion in nature does not operate at efficiencies of 100%, unfortunately. There are always some fundamental losses at play. Nature is very cruel in that sense. The losses in the hydraulic power system are mainly caused by three factors. The first loss mechanism occurs when the turbine converts the kinetic energy of the water to rotational or mechanical energy. The fundamental laws of physics, like the conservation of the energy and the second law of thermodynamics, prevents the turbine operating at 100% conversion efficiency. As example, a typical Francis turbine can operate at efficiencies of 90 up to 95%. The loss mechanism of turbines are typically hydraulic losses, vortex rope formation, leakage losses, mechanical losses, and incomplete velocity reduction. Secondly, some losses occur in the generator, where mechanical energy is converted into electrical energy. These losses are related to the electrical resistance losses, magnetic losses, and mechanical friction losses. Thirdly, some system losses like water flow losses loses some of its energy due to the friction losses in the penstock and electrical losses in the transformer when the electrical energy is converted to a higher voltage. The final annual energy yield, or the capacity factor of the hydropower plant, can be strongly influenced by the weather conditions, especially the amount of precipitation, snowpack melt, and the amount of water within the catchment area that is evaporated and absorbed by the vegetation before being utilized by the hydroelectricity dam. This affects the available water flow and the height difference of water, and consequently the potential energy that can be used. Therefore, the power output of an hydroelectricity plant can vary in time and even be seasonal dependent. Another factor that can impact the energy yield and capacity factor is that the power plant, like many systems, has a certain downtime for maintenance and repair. Furthermore, the storage capacity of the top water reservoir can be reduced over time due to sediment accumulation, referred to as siltation. Next, let's work through an example. We will take as an example the Itaipu Dam on the border of Brazil and Paraguay. The Itaipu Dam is the second largest hydropower plant on the planet. The dam is responsible for 90% of the electricity supply in Paraguay and 10 to 15% of the supplies in Brazil. It has a total installed generation capacity of 14 gigawatt based on 20 turbine generator units of 700 megawatts. The typical precipitation in the region around the Itaipu Dam is around 1500 millimeters of rain per year, and there is no meltwater from mountain snow or glaciers. However, vegetation and evaporation is responsible for 83% of this water to be lost and is not collected by the water reservoir behind the dam. Additionally, the height difference between the source and the outflow of the dam is 118 meters. The catchment area of the Itaipu Dam is 1,350 million square kilometers, and the area of the reservoir, reservoir that includes the dam and artificial lake is 1,350 square kilometers. With this information, we can calculate the energy potential in joules. First, we will determine the total mass of the water. 1,500 millimeters of rain per year is equal to 1.5 cubic meters of water per square meter, and including the losses, only 16.7% of the rainwater is collected by the reservoir. By multiplying that with the density of the water, we get per square meter of land there is 250 kilograms of water per year. Using a height of 118 meters, we will receive 289 kilojoules of potential energy per square meter per year. This is equal to 80 watt hours per square meter in reference to the entire catchment area. The total yield of the hydroelectricity dam would be 0.08 kilowatt hour per square meters per year, multiplied by the surface of the catchment area of 1.35 million square kilometers, which makes a total of 108 terawatt hours per year. Note that this number does not include the conversion efficiency of the hydroelectricity generation system itself. Keep this number in mind. In a minute we will compare this number with the real yields achieved. If we express the area performed in power per area in reference to the catchment area, we get something like 0.0091 watt per square meters or 9.1 milliwatt per square meters. If we have to compare the power density of the hydroelectricity with other technologies, which we will discuss in the upcoming video lecture, it's more relevant to only consider the aerial footprint of the water reservoir and the dam. In this case, we arrive at a power density of 9.1 watt per square meters for the Itaipu Dam. This value can vary from hydroelectricity plant to plant, depending on the depth of the reservoir and the hydraulic head. As comparison, typical values range from below 1 watt per square meters up to 10 watt per square meters. This shows that the Itaipu Dam is a high-performing dam. Let's consider the real energy yield of the Itaipu Dam in the year of 2015, which is 89.5 terawatts. This is 83% of the theoretical yield value calculated a minute ago. If we divide the 89.5 terawatt by 14 gigawatt times the total hours in a year, we'll receive a capacity factor of 72%. It's the power plant's actual energy output over a period to its maximal potential output if operated at full rated power continuously. So you could say on average the Itaipu Dam in 2015 produced electricity at maximum capacity during 70% of the time. Let's check this out for other years. This graph shows the installed capacity over the years and the full 20 turbines of 700 megawatts which were installed, making it up to 14 gigawatts. In black, the annual electricity generation from 2007 up to 2025 is shown expressed in terawatts. Using these values, we can calculate the capacity factor as shown by the blue circles. As you can see, in the period from mid-90s to mid-10s, a capacity factor between 70 and 85% was achieved. Whereas in the last years, the capacity factor has dropped to 55 to 70%. The main reason is the severe and prolonged drought conditions in the Parana River basin, a lack of water availability to fill the reservoir and drive the turbines at full capacity. Here we present the carbon footprint and the total life cycle greenhouse gas emission per unit of electricity generated. The medium carbon footprint for hydroelectricity dams is around 24 grams of carbon dioxide equivalent per kilowatt hour generated. That is a factor 34 and a factor 21 smaller in reference of generating electricity from fossil fuels like coal and gas, respectively. The energy payback time is the duration that a renewable energy system must operate to generate the same amount of energy that was consumed during its life cycle, including manufacturing, installation, operation, and disposal. For hydroelectricity, the typical energy payback time is 4 up to 11.5 months. The energy return on the energy invested is the ratio of usable energy delivered during the lifetime of the generation system divided by the energy consumed by the generation system during its life cycle. If we consider a lifetime for a hydroelectricity dam of 100 years, it means that the energy return of energy investment can be around 100 to 200. So, what exactly are the advantages and the challenges of hydroelectricity? One way of looking at a reservoir is considering it as a storage of potential energy. At moments when the production surpasses the demand, the water in the reservoir can be pumped to a greater height. Then, when demand is higher, the water can flow down again to produce electricity. Therefore, you can easily control the power output in a hydropower plant without losing valuable potential energy. A hydropower plant can therefore provide support to grid and also supply a stable power output. Another advantage is its long lifetime of 30 to 100 years. Therefore, despite the large concrete constructions that needs to be built, a hydropower plant can have a relatively low carbon footprint. However, hydropower doesn't work without a very large water reservoir. Such a reservoir has a huge impact on the local flora, fauna, and landscape. In case of a really large hydroelectricity project, the local climate could even change due to the change in the water cycle. As a result of the impact on the surroundings of the dam, the global potential of new hydropower is relatively limited. Nevertheless, hydroelectricity is still the biggest contributor to renewable energy electricity with a global installed capacity of 1,443 gigawatts, producing approximately 4,587 terawatts of electricity. If we take a world population of 8.2 billion people in 2024, this results in an energy density of 1.53 kilowatt per person per day. Let's put these numbers in reference to world's primary power demand of 90 terawatts in 2024. With this map, we can visualize what surface area is required to cover this demand with the technology discussed in each video. So using the catchment area as a reference, hydroelectricity has a surface power density of smaller than 0.0 watts per square meters. To generate 19 terawatt in an equivalent hydroelectricity, at least 37% of the planet's surface should contribute to the catchment area, the size indicated by this white area. Note that this is larger than the total land area of planet Earth, which is around 30%. However, if we consider the total area needed in the form of dams and only the water reservoir, typical surface power values range from 1 watt per square meters up to the 10 watt per square meters we discussed earlier. Now, so let's assume on average 3 watt per square meters for electricity dams. The needed dam and the reservoir area would then be 1.2% as represented here by the green area. The most important factors in producing hydroelectricity are the amount of water and the height difference. We have discussed the important performance metrics of the hydroelectricity plants. We have discussed the conversion efficiencies, the energy Z's, the typical capacity factors, which also can vary over the years, aerial power density, the common footprint, and energy payback time. Hydropower can provide a constant source of energy and can even function as an energy storage source. The environmental environmental impact of a hydro plant can be quite significant, however. In the next video, we will discuss another renewable energy source, wind energy. So see you back in the next video.